Allison. Thanks to everyone for coming in on Friday and viewing this talk. So, as Allison said, I'm a visiting research professor here. That means that I've actually been here for about 4 years now at LSRI. And one of the first projects that I started working on was this Next Generation Science Standards Assessment project. And so this is exciting for me to be able to present this work here today. This is the first time I will have been presenting this work in this setting, the first time that I'll be presenting empirical data on this work. Most of what I've done before in presenting around this work is really around the nuts and bolts of how we design those assessments. What I thought I'd do today was take a step backwards and think about how we validate those assessments. And really think about two ways in which we're validating those assessments. One, through the structured design process that we're using to develop the assessments, and then secondly, through the measurement models that we're constructing around those assessments. So that's sort of the general overview that I'm going to be talking about today. I do want to acknowledge a couple people and a couple organizations. So this work is funded by the National Science Foundation and the Gordon and Betty Moore Foundation. And this work is collaborative work. It's interdisciplinary with multiple institutions. So we're working with individuals at the Michigan State University's Create for STEM Institute, SRI Education, here faculty and researchers at LSRI, and then also individuals at the Concord Consortium. So we have a mix of individuals from all the way from senior faculty all the way down to undergraduate students that have been involved in really a critical part of this work. So what I'll do today, I'll start off by talking about multidimensional competencies, what those mean and how those are articulated in the next generation science standards. I'll briefly take a little sidestep and talk about how you validate assessments and think about validating of assessments for classroom instructional purposes. And then I'll talk about a principal design approach that we use in this project to develop the assessment tasks. That's evidence-centered design. I'll then go through the measurement model that we're using to sort of analyze these empirical data that we have, and then talk about some conclusions and implications. So that's the plan. I should say, if you have any questions, feel free to bring those up during the talk. You don't have to save them to the end. I'd like this to be a little bit of a conversation that's going on. All right, so in the last decade or more, there's been an increasing sort of prevalence and recognition that proficiency in science and engineering requires competence with the practices of science and engineering. And I think this quote from the National Research Council really sums it up well, that science involves a set of communal practices that establish, extend, and refine that body of knowledge. And so what we should be thinking about is that for students to be proficient in science and engineering, they should engage in these practices. And they should do this for two reasons. They should do it first as a means of developing their conceptual understanding, but secondly as a means in and of itself. So the capability of engaging in these practices is critical for actually developing capacity to do science and to do engineering. So this emphasis is motivating reforms in a variety of different areas, one in K through 12 education, and we can see this through the work of the College Board in redesigning the advanced placement courses and their role of bringing practices into the testing and the curriculum for those AP courses. In the framework for K through 12 science education, which then got manifest in the next generation science standards. And increasingly, we're seeing over the last 5-10 years, really a focus on doing this work in undergraduate learning environments as well. And someone sitting in the front row here, Don Wink, I know is doing this with some of his chemistry faculty in really thinking about the practices that are involved in chemistry and what students should be engaged in. So I'm going to use this term a lot, practices, and you might be wondering, what are these practices? So I'll just give you some examples of some of these practices. Developing models to explain phenomena, that's a practice, or using those models to make predictions. Engaging in evidence-based argument is another practice, or engaging in critique of arguments and counter-arguments, that's another one. Analyzing and interpreting data, planning and conducting investigations. All of these are the practices of sciences Practices of engineering include also developing models, designing solutions to problems, analyzing and interpreting data. So I'm going to focus on the next generation science standards because that's where a lot of the work that we're doing is positioned. So the science standards are unique in that the new version of these standards really expresses themselves as what is called performance expectations. So here's an example of one performance expectations. Students who demonstrate understanding can develop and use a model to describe how the total number of atoms does not change in a chemical reaction, and thus mass is conserved. So these performance expectations are multidimensional, or sometimes they're referred to as being three-dimensional. And that's the case because each performance expectation is a combination of at least one disciplinary core idea, science or engineering practice, and one cross-cutting concept. So if you look in this performance expectation, you can sort of see the disciplinary core idea. So we're talking about the number of atoms, whether those are changing in a chemical reaction, and the conservation of mass. There's also a science practice that students are developing and using a model. And then there's also a cross-cutting concept. In this one, it's cause and effect. So how the total number of atoms does not change the effect by a chemical reaction, and thus mass is conserved. Now, one way to think about these three dimensions is as a rope with different strands. And really what we want to be doing is integrating those different strands together. And we want to be doing that because that forms a stronger body of conceptual knowledge because it's all integrated together, and it's more robust and more able for students to then put that knowledge into use, into practice. So we have a project here funded by, like I said, the National Science Foundation and Betty and Gordon Moore Foundation to develop assessments for the next generation science standards. And this is to develop a couple of things, actually, not just to develop assessments, but to develop a principled approach for creating these assessments and for creating assessments that are useful for teachers in the classroom. So assessments that can be used formatively by teachers to see whether students are making progress towards achieving those performance expectations. Then what we want to do is use that approach that we're developing to then develop, test, and validate technology-enhanced assessment tasks and rubrics. And we're doing this in the context of middle school science. But the idea is that the K through 12 science standards spread across all of those grades, and that this principled design approach could be used in the elementary grades, it could be used in the high school grades as well. And then finally, we're engaging in a co-design process with science teachers to develop guidelines and strategies for classroom use. So again, I want to be, this is really important. I want to be positioning this as how teachers can use this in the moment with their students during the semester to see if students are making progress, not as a more summative set of tasks that they would use at the end of the school year. So to date, we've created over 100 assessment tasks. Those are in both the physical and the life sciences. We put these on what we call the online portal, which hosts those technology-enhanced assessment tasks. That portal is available to the public, so it's free for teachers and students to use. And we're in the process of putting up rubrics on that portal as well. And then we're also in the process of validating these assessment tasks. So you might be wondering what these assessment tasks look like. So I'm going to present one assessment task here. Let's see if this video actually works. Okay, so it's a little bit hard to see, but there's a video that goes along with this task. Students would actually watch the video here. In the video, there's bubbles that are coming up from the two terminals of the battery. And this is the task that students get. So, excuse me. So the scenario is Rosie put a battery in a beaker of tap water. She observed gas bubbles coming from the positive and negative ends of the battery as shown in the video. She tested the bubbles and found that some of the bubbles were made of hydrogen gas and some were made of oxygen gas. Draw a model that shows the chemical reaction of water changing into hydrogen and oxygen gas. And then, from your drawing, describe what happens during the reaction to the atoms of the water molecules and how your model explains why mass is conserved during this reaction. there's a spot for students to actually draw their model, a little note to them to make sure to add labels to the model to explain what's happening. They're given this sort of key of molecules, so they don't have to know what the oxygen or hydrogen molecules look like, or even what the water molecules look like. They can use this key as a sort of scaffold for developing them. They would develop and draw this model here. What's not shown is that they get a text box where they can then describe what's asked of them from their model. So that model then has a sort of textual description that they provide. So I'd like y'all to take a minute and actually think through how you would answer this task and talk with a partner, so just someone maybe in your row sitting with you or someone behind you, and think about a couple things. So when you're thinking about how you'd answer this task, think about one, what would your model show? And then what would your description of the model include?
You got us too involved.
I know, that's great. That's great. But does someone want to volunteer and talk about what they were, some of their discussions that they were having? So, what would your model show? Did anyone?
You want to make sure that in the end you have the same number of hydrogens and oxygens as what you started with.
Okay.
And so you would use the little draw tool. So if you started with 2 waters, then when they break apart, then you need to make sure that they're not connected anymore. And then you have 4 hydrogens, because if you started with 2 waters, you started with 4 hydrogens.
Right.
So you would have your 4 hydrogens, and then you would have 2 oxygens if you started with 2 waters.
Okay, great. So that's what the model would show. That's a good description. What Crystal was saying was, in order to get the conservation of atoms here and conservation of mass correctly, what you have to do is you actually have to start with at least 2 waters, so that you can then have the 2 oxygen that are going to appear in the final equation. And you can really do this as multiples so that you can have all these. So what would your description of the model include then? Yes, Laura.
Wouldn't you have to then explicitly say why 2 waters became became 1 oxygen molecule and 2 hydrogen molecules? Because if you're trying to explain why it shows conservation of mass, then you'd have to explicitly say, like, my model is drawn this way in order to keep the number of oxygen and hydrogen atoms the same before and after.
That's great. So including that feature about keeping the number of atoms the same before and after the reaction. Did you have a question, Susan?
I do.
Okay.
Why does this happen at all?
Why does the phenomena happen at all?
You have to mention you introduced energy into the system to break apart the bonds of the water molecules and be able to reform into the 2 separate gases.
And how is energy introduced into the system?
The battery.
The battery.
So, but if you have, creative kids, they'll do all sorts of things that have nothing to do with those drawings that we all said. They'll look completely different. And the smarter ones will say something about, well, if it's a lithium battery, we should have fire going on.
And we also had debates in our team developing these. We originally had it as just a beaker of water. We added in tap water there because of the impurities in the water that allows that to happen.
That allows what to happen?
The chemical reactions to be happening. Yes,
So
Don.
does the battery leak?
No, the battery isn't leaking.
I don't have any understanding of why putting that battery in that water makes anything happen.
Let's see if Don wants to explain.
Well, what I was going to ask is, does the model have to account for the battery?
Good question.
And how does the model account for the battery?
So the model that we are looking for does not account for the battery. So one of the interesting things that this discussion is bringing up is the NGSS is really focused on having students make sense of phenomena. And so this is a great example of some phenomena that is happening. But that phenomena is sort of an engaging phenomena. But what's happening and what we're really focusing on is solely this setting up this idea of the chemical reaction and the conservation of matter. And so it's not that we're having them model the actual scenario and phenomena. They're just modeling the chemical reaction that happens.
So, okay, but, I mean, I'm just gonna
Sure.
drive this. There are two chemical reactions occurring in that beaker.
Okay.
One of which has to do with the water at the surface of those electrodes, and the other within the battery.
And that chemical reaction has to be happening in the battery in order for those bubbles to form.
And there are a couple, right, and so again, I know exactly what you asked for with the developing of the model of the chemical reaction of water, which allows one to discard the battery as a factor. But the phenomenon has the battery in it.
Mm-hmm.
And so what I hear you saying is, let's give them a phenomenon in which we're only attending to a portion of it.
Yes. That is what we're doing in this task. And you might have some concerns about that. Yes.
In a sense, isn't that what you're always doing? Like any complex phenomenon, and looking at, it may be a bigger subset or a smaller subset, but like anything that you're looking at in science, you're picking a subset of the phenomenon to be looking at. You're just specifically saying this is the subset to look at. The kids don't get to pick.
And same with the model, right? You're defining a portion of the phenomena and you're modeling that portion of it, you know, and you're defining the boundaries of that model as well.
So,
Yes, Laura.
One thing I found interesting about this is the DCI, the content piece, part of it is conservation of mass. And what I found interesting is this doesn't ask students to identify that mass is being conserved. They're asked to they're told
Mm-hmm.
explain why mass is conserved during this reaction. So it was interesting just to me that instead of asking them for a fact or a piece of information, is mass conserved or is mass not conserved, they're asked, in this case, you're specifically asking, how does your model show this thing that we're reminding you it's happening?
That's right. That's right. And that was by design. But that's a good observation. Raymond?
Is there a lid on that beaker?
There is not in the video, no.
So, in fact, the gas escapes.
Yes.
So, that mass is somewhere in the universe, but if they were to put this on a scale, they would notice a change.
Yes.
So
I think so.
You've got to be able to, so what happens if a student responds to, I read this paper you guys passed around and didn't really account for this. What happens if a student says, well, the gas escapes? So in fact, mass is not conserved in this container.
Well, so in the chemical reaction, so it says why mass is conserved during this reaction. So it's still conserved during the reaction, regardless of where those bubbles go.
Okay. But I can see students heading that way with those kind of questions.
Yeah,
But
you can
again,
see-
you're bounding the phenomenon in a particular way.
Yes. Yes. One more from Susan, and then we're going to go on.
I just want to remind you that how this maps
Mhm.
to the multi-dimensional, to the 3 pieces.
Yeah, that's great. And so what I did here is I color-coded these. So the blue is the color coding that the NGSS uses for science and engineering practices. The orange is the disciplinary core ideas, and the green is the cross-cutting concept. And I misspoke earlier, the cross-cutting concept in this task is not cause and effect. It's conservation of mass and flow of energy. So mass conservation is one dimension. Creating a model, using that model to explain something is another dimension. And then this idea of chemical reactions and the atoms regrouping in these chemical reactions is another dimension. And what you would like to see is not only that the task and the prompt has those 3 dimensions, but that the student response has those 3 dimensions also. And so what we'll look at a little bit later is we'll start looking at some student responses also and see how those 3 dimensions come out and how we're representing those. So we do have a lot of measurement challenges that are, so it's challenging just in and of itself to develop a task like this. And part of the reason it's challenging was because of when you're situating it with the real phenomena, there's a lot of science that's going on in the background that might be beyond the grade level expectation of the students. So that's another reason we're trying to bound this around just chemical reactions, because it's in the middle school level and that's what they're responsible for knowing. But there's also some challenges that come about from having these multiple dimensions. For instance, having practices and conceptual knowledge together. And how do you measure students' knowledge, skills, or abilities with these dimensions? Well, one approach might be to measure them all individually. So get some sort of measure about how they can do a practice, get some sort of measure about what they know about this. So, do they know that chemical reactions regroup? Can they build a model? And do they know mass is conserved? That would be sort of an example of separating those out and reporting it out. We don't want to do that. As a team, we've decided we want to have these 3 integrated together, like that rope analogy that we were looking at. So instead, we want to maintain this integration, but then the question is, how do we know this approach is producing tasks that are valid for their intended use? So how do we know it's actually maintaining that 3-dimensional nature and actually getting at the practice of using models, getting them to represent or report on the disciplinary core ideas, and also using that cross-cutting concept? So our solution is to use a principled design approach and measurement approaches, both of which retain the integration of these 3 dimensions. So let me take a sidestep and talk a little bit about validating assessment tasks, and then we're going to go back into how we do that in the design process and the measurement process. So we view validity as an argument, and that argument involves specifying the claims regarding the use and interpretation of test scores, and then evaluating those claims in terms of their clarity, their evidence, their logical coherence, etc. So a couple things to note: validation is a dynamic argument, and it changes with additional validity research. Additionally, it is not all or none. It's a matter of degree, and that matter of degree depends on the context and the use of those assessment tasks. So we are also in this project adopting a validation framework for classroom assessment tasks that looks at 3 different aspects of validity. So a cognitive aspect of validity, and this is basically, does the assessment recruit the intended knowledge and skills? So for instance, it would not include construct irrelevant variance in students' performance on the task. An instructional aspect of validity, that is, are the assessments able to provide useful and usable information for teachers to allow them to make instructional decisions? And then finally, an inferential aspect of validity, and that is the assessment tasks and the data that you can collect from those are amenable to quantitative modeling, especially ones that enable diagnosing problematic thinking of the students. So we're going to return to these 3 aspects of validity when we're looking at different types of evidence for them. So I'm going to now focus on talking about our design approach for validity. And so one piece of validation evidence is actually the design approach that is used and whether it allows for an explicit articulation, a transparent rendering of the development process that's been used to develop these assessment tasks. And to do this, we use a principled design approach that's called evidence-centered design. Sometimes it's abbreviated ECD. And this is really a method of backwards designing assessments in which one makes claims about students' proficiency. Then one articulates the evidence for those claims that would be found in student response products. So basically, what a student could say or do that would give you evidence for that claim you're making. And then we take those evidence statements and we actually use those evidence statements to create assessment tasks that are going to elicit that intended evidence. So this involves multiple stages of work, and I'm going to focus on 2 stages, domain analysis and domain modeling in this talk. But this is the full design process that we use, and let me just kind of run through it real quick. We start off by identifying the standards that we're interested in measuring. And again, in the NGSS, these are performance expectations. Then what we do is we unpack each dimension separately. And then we use that unpacked each dimension separately to then build those back up into an integrated dimension map. And this is basically like a concept map of what has to be learned by students. We use that to create learning performances. And if you read the paper for Journal Club, then you would have learned about the learning performances. And this is basically just a way of defining a family of tasks that are all related to a central claim about student proficiency. From there, then we specify task design patterns that have a number of features in those design patterns. And then, and only then, at the very bottom, do we get into developing tasks and rubrics. So we do a lot of work before we even jump into developing these assessment tasks. This kind of looks like a linear flow. It's not. All of these arrows are really double-headed and they're going back and forth as we do this development process. But I'm going to focus first on this domain analysis section up here and the unpacking, and then I'm going to focus on the domain modeling section here. I'm not going to get into too much on how we actually develop the tasks and rubrics themselves in this talk. So let's think about the domain analysis and unpacking. That's what we do. So here is, again, a performance expectation. Now this is a different performance expectation than we've been talking about. So students should be able to develop a model that predicts and describes changes in particle motion, temperature, and state of a pure substance when thermal energy is added or removed. So if you're looking at that and thinking about, okay, I have to design some assessment tasks around that, you might realize that that's really a dense statement of what students have to know. And so that's why we want to unpack those. So that unpacking process enables you to identify the essential elements of each dimension. It allows you to pinpoint the knowledge and capabilities that students need in order to use and apply that given dimension. And it also allows us to describe level of performances for those dimensions at the grade level that we're interested in. So remember, again, we are looking at middle school students. So when we're having them do things like developing models or thinking about conservation of matter, that also has to be unpacked at the level of the middle school requirements for how they should be able to use those. So this process is really critical because it promotes consistent use of the dimensions when you're developing those assessment tasks. So when you're developing 100 or so assessment tasks, you really want to have some principled way to make sure you're using cause and effect the same way in all those tasks, or you're using developing and using models the same way in all those tasks. And it really makes those essential elements of the task come to the forefront and make sure that they're really brought about in each of these tasks. So let me give an example of how we do this unpacking. I'm going to give it for just one dimension, how we unpack the disciplinary core idea. And I should say we do this unpacking with disciplinary experts. So what we do is we have experts that have the requisite knowledge in physical science or life science that act as sort of our critical subject matter experts when we're trying to elicit all the knowledge and represent that knowledge that students need to know. That's critical because as you probably would have guessed from me presenting the battery task, I'm not an expert in chemistry, and so we really have to have these domain experts with us involved in this assessment development process. Yes.
Since you were also discussing the levels of students, do you bring in education, like experts of that level of education?
Yes, so we actually bring in individuals that have expertise at educating students of that level. We do that in 2 ways. And so sometimes we have that in the domain analysis phase, sometimes we have that in the task review phase. And so that's not something that I'll be talking about today, but a critical aspect of developing valid tasks and another source of our validity evidence is having external expert reviewers reviewing these assessment tasks. And we try to make sure that at least one of those external reviewers has the experience with teaching and the expertise in teaching at this level.
Okay.
Yes, Raymond.
So you have a very highly structured environment you're building here. How do you balance that with the idea that students should be able to, develop their own sort of inquiry into an area and use their imagination, pursue lines of thought that perhaps aren't exactly in your structure, but would enable them to learn more themselves?
Yeah, so that's a great question. So how do you really, motivate and enable the students to be driven in an inquiry basis to be using these disciplinary ideas? And that's a mix of instruction and assessment. So we want to make sure that the assessments give them a chance to do things that are similar to inquiry, like developing and using models, developing arguments, explanations, developing or designing procedures, investigations, things like that. So the assessment tasks bring those in, but a critical part of this larger learning environment is the curriculum and the instruction that's paired with these assessment tasks that actually allow that to occur. So this is an example of the unpacking. We elaborate elements of the disciplinary core ideas. We describe the boundaries of proficiency. So here's a caveat. Students don't need to understand heat as the process of transfer of thermal energy or the role of the rate of thermal energy transfer. We explicitly talk about the prior knowledge that we're expecting students to come into. So they should know from grade 5 that matter is made of particles too small to be seen. And then also we articulate student challenges, which is I think something that sort of Laura was getting at, which is how do you sort of bridge this with the instruction that's occurring and the knowledge of where students are likely to be tripped up in learning about this. So we do the same unpacking for the other 2 dimensions. I'm not going to go into those in this much detail, but then what I'll show you is that we use this unpacking to then do alignment. So we want to make sure that we have an alignment of the requisite knowledge, skills, and abilities that are needed for each of these dimensions, and that those come out in the assessment tasks that we're developing. So here's an example of a claim about students. Students who demonstrate understanding can develop a model that explains how particle motion changes when thermal energy is transferred to or from a substance without changing state. So for those of you who read the paper, this is a learning performance. This is smaller in scope than that larger performance expectation. And so it focuses specifically without changing state. But what you can see here is what we call an unpacking alignment table, where we take all the knowledge that's required of students to be able, that we hypothesize to be able to do this, all the knowledge that underlies it, and we basically make all that knowledge explicit. And then we can use this as a check when we're developing assessment tasks to make sure that students are required in that assessment task to specify elements of the model, to represent the relationships or interactions among the model, to use the disciplinary core ideas, to use that cause and effect there. So this is all part of the domain analysis still. But what we also do is domain modeling, and I'm going to focus on one aspect of domain modeling, creating what we call task design patterns. And so design patterns are used to define a family of related tasks that focus on the same knowledge, skills, and abilities. They define characteristic task features. So every task within this family is going to have these features. And then they also define features that can vary across tasks within a family, within the same learning performance. So we do this so that we can create a variety of different tasks that are all getting at the same claim of student proficiency. And we can use this to vary the level of scaffolding that we provide for students. So here's an example of one of our design patterns. It starts with a claim about student proficiency. Students can develop a model of chemical reaction that explains new substances are formed by the regrouping of atoms and that mass is conserved. So this is the claim of proficiency that was in that battery task. And then we write an evidence statement. It's abbreviated here. This evidence statement also actually goes longer. But what's important here is, again, we're defining what would be evidence that students have this proficiency. They have to have a model with these elements. The relationship of the elements have to be here. We define what we are hypothesizing as focal knowledge, skills, and abilities that are needed for students to be proficient and to provide this type of evidence. We define the characteristic task features. So every task in this family is going to have a tool that allows students to either draw or somehow represent the model. The scenario is going to present a chemical reaction, and that scenario is going to involve at least two substances. You're going to have one or more substance before the reaction and one or more substances after the reaction. But then you can vary the tasks in the family by varying the number of substances that occur before or after the reaction, or varying the number and types of atoms that occur. And then we also have other variations there. We use varying types of tools that they use to make these models as well. So I'm going to delve in a little bit more on the focal knowledge, skills, and abilities here, because those are really critical in how we assess the tasks, how we evaluate those tasks, how we develop rubrics, and for the scoring models that we create. So the focal knowledge, skills, and abilities, FKSAs, these are multi-dimensional statements. So the focal knowledge, skills, and abilities themselves maintain that integrated three-dimensional nature. So what I've got down here are 3 examples of a focal knowledge, skill, and ability, and they're color-coded. So you can see that within each bullet here, there's always at least 2 dimensions. Oftentimes there's all 3 dimensions in there. These always are defined in terms of knowledge and use. So that means students are doing something with their conceptual knowledge. They're putting it into practice. So again, these are worded as their ability to support model use or to develop a model themselves. These KSAs are the smallest grain size of the knowledge skill unit, and they're present, this same set of focal knowledge, skills, and abilities are present in all tasks from the same family of tasks. And then what we do is we use these to create rubrics where we can score each focal knowledge, skill, and ability individually, and that allows us to improve the diagnostic capabilities of the assessments because we're able to see if students are having difficulty with showing that the chemical reaction conserves atoms, or with explaining that the chemical reaction involves regrouping of atoms, or maybe they're having difficulty not with their explanation, but in developing the model itself. Yes, Monica?
Okay, so the FKSAs are 3-dimensional. I'm just trying to think about the hierarchy. So there's LPs, which are 3-dimensional. There's FKSAs.
LPs are learning performances.
Right. And
Right.
PEs are 3-dimensional. LPs are a broken down version, but that's also 3-dimensional, of a single PE. I'm just trying to figure out how the LPs and the FKSAs relate to each other.
So let me show you a visualization that might help, or it might make things much more confusing. So this is in my extra slides, which I wasn't going to go into. Let's see. So if we have a PE up here, students develop and use a model to describe how the total number of atoms does not change in a chemical reaction and thus mass is conserved. We have a set of FKSAs that underlie each of these learning performances. So those are sort of the compositional elements of those learning performances, and those are shared amongst multiple learning performances. So a performance expectation has multiple families of tasks. Those families have multiple tasks, and then sort of the framework, the skeletal structure that underlies those learning performances are these small grain size units, these focal knowledge, skills, and abilities.
So if I have a rubric for task 21,
Uh-huh.
which is connected to 2 FKSAs, do I So, okay, so all the tasks under LP6 can be, the same rubric can be applied to all of those tasks because they share.
The same foundational rubric is used. We end up making task-specific rubrics, but those rubrics all share the same features because they're all from the same family. So they always have two aspects of scoring, one aspect around this FKSA and one aspect around this FKSA. And all the tasks there are going to have that same structure.
Okay, so how did you get from an FKSA into an LP?
So that's how we do, that's part of our domain modeling approach.
Okay.
And that's actually not something that I'm going to talk about today.
All right, I'm just curious.
Yeah.
Because there's so many three-dimensional things.
Yes.
I'm trying to figure out what it is.
Yes. And, you know, it's by design, not by design to make it confusing, but by design to have these 3 dimensions in all of these different levels so that we can maintain that integrated use of those 3 dimensions. Raymond?
This picture, the arrows go the opposite way of the one in your paper on page 8, where you
Yeah.
have the learning performances feeding into the FKSAs.
That's correct. There are 2 different representational schemes. I myself prefer this one because I think it shows that the FKSAs are not a property of the learning performance themselves, but they're essentially the backbone that's used to create that learning performance.
Also, it seems like the wording of the FKSAs are about the ability to do something
Yes.
three-dimensional, whereas the LP, I don't know, it just seems like the wording is different. I was just trying to figure out how to characterize those different, the ways in which the 3 dimensions is kind of weaved throughout those 2 types of statements.
Yeah.
We don't have to talk about that.
Okay. Let me try to go back here. Okay, so what we've seen so far is we've seen the evidence-centered design provides design-based evidence for claims of cognitive and inferential validity. However, those claims also require empirical evidence. So it's not enough to say we have a great, transparent, confusing design process. We also have to get some empirical data that supports these validity arguments we're trying to make also. Just as an aside, I want to say that this is difficult to do in classroom use because measurement models are really built around large-scale assessments, and they're not built for using small sample sizes. And by small sample sizes, I mean both a small number of students that you would have in a classroom and also a small number of tasks that students complete. So just the fact that we're able to fit some measurement models to these data is kind of a nice finding in and of itself. Before I move on though, we've had some great questions before. I'm changing gears a little bit, so I want to see if we have any questions that are still remaining. Yes, Laura.
Quick question, just to wrap up what they were asking about with the FKS something or other
A's.
and the LPs. Which do you usually create first?
The learning.
Or does it sometimes go one way, sometimes
I mean,
the
it
other?
goes back and forth. So it's
Okay.
it's a process of creating the learning performance and the FKSAs together, refining the learning performances, refining the FKSAs.
Thank you.
Yeah, that's one of the spots where it's really a lot of iteration back and forth. Okay, so I'm going to present some empirical data that we collected. So this data was collected during 2016-2017. The students were from the 6th and 7th grade across 3 different states and 3 different school districts. All participating teachers were using an iQuest curriculum, which emphasizes science practices of modeling and explanation and the disciplinary core ideas. So we have some sense that students had an opportunity to learn these multiple dimensions in which we were collecting this data from. So we had 887 students complete tasks from the chemical reactions topic, which actually spans 2 performance expectations. Students get assigned a booklet of 6 tasks. The majority of those tasks are from different families, different learning performances. And then we selected a subset of students for analysis And by selecting that subset, we're also, also selecting only 8 tasks. So we're looking at 8 unique tasks across 3 different booklets that we're analyzing. Those tasks come from either this performance expectation or this performance expectation. All right, so in order to delve into this a little bit more, I want to do an introduction to item response theory, since that's what we're using to analyze these data. So classical test theory is a way of representing the observed score. It's a model of the observed score where you have a true score and then some unknown error component in there. And so any observation of total score you get has, somewhere where a student is on a latent variable and then some amount of measurement error around that. In contrast, item response theory creates a model of response on a given item. And that response on a given item is a function of item and person features. And one of the nice features of item response theory is that you're able to put items and persons on the same scale. And let's take a look at what that means to have them on the same scale, and then also break this formula down a little bit more so it's a little bit more intelligible. So again, this is the probability of getting a given response on an individual item. So item is subscripted with I, student is subscripted with S. So if we can read this, it's probability that a student's response, that an individual student's response on an item is 1 being correct, is conditional on that student's ability level. We're going to represent their ability level with a theta, and the difficulty of the item, which we'll represent with a beta. And then we can actually calculate that function using the constant e, raising it to the exponent where we have these two, the feature of the item and the feature of the person in that exponent. So then what we're able to do with that function is create a measurement model where we are graphing the probability of a correct response on an item as this S-shaped function, which is what you sort of typically get. This is sort of the ideal type of item characteristic curve you would get. So let's break this down. You can think about a threshold of getting an item correct or not. So if you are if you're given an item that you're just right at the threshold of being able to solve, half the time you might get it right, half the time you might get it wrong. Okay? So take a spot at 0.5 in the probability of getting that correct spot, then drop a vertical line down, and then you can see what that item's theta level is, that item's ability level. So again, theta here is this latent construct. We're just going to say, in this example, the latent construct is knowledge on that chemical reaction topic, those 2 performance expectations we gave. And now we can think about students as being somewhere on this latent trait. So if a student knows more in this area, they're going to be further to the right. If the student knows less in the area, they're going to be further to the left. And same with item difficulty. So if the item is more difficult, that's going to shift this curve to the right, which means that students have to have a higher theta, a higher ability level, to be able to solve that at 0.5 or anywhere on that curve. If that item is easier, oops, I'm going the wrong way, then it's going to shift to the left. Yes?
With using IRT on these, are you using it on the item as a whole or on individual pieces of the rubric?
We're using it on the item as a whole, but I'll show you how we use the individual pieces of the rubric to create that on the item as a whole.
Thanks.
Mm-hmm. Okay, so what I just talked about was thinking about item response theory in terms of dichotomous responses, them being either right or wrong, 1 or 0. You can extend item response theory to also include partial credit responses, where a student gets, maybe total score on that item could be 4, but they could get anywhere between 0 and 4 on that item. The curves look a little bit different when you do that. So now what's happening is that you've got 3 curves one curve for each score. So this item has a possible score of 2, 1, or 0. You have a probability function for each of those responses. So the probability, you can think about this as if a student is, say, -3 in their ability, their probability is going to be highest that they're going to get 0. If they're at about 0, their probability is going to be that they get 1 partial credit. If they're at, say, +3, then their probability is going to be that they're getting full credit on there. So this is a very neat picture in like the type of curves that you would like to see, but they're not always as pretty as that. So sometimes you get curves like this, where notice there's a little bump for here for an item where a student gets 1. Notice on across this latent trait scale, there's not really any latent trait where it's going to be a probability that a student gets 1 over any other response. So if you were interpreting this, it's likely that students are going to either get full credit or almost full credit or nothing. And that shows up as well. So let's actually look at some of these tasks and look at how the item functions look. So I know the font is kind of small here. Let me read out this task. And I just want to say this is in the same family of tasks as that battery task that we looked at already. So in some factories, people use chemical reactions to produce new substances. Methane can be chemically reacted with water to produce hydrogen and carbon monoxide. So here's the reaction: methane plus water leads to hydrogen plus carbon monoxide. Use atoms and or molecules from the left side of the tool to create a representation, a figure of the reaction between methane and water to form hydrogen and carbon monoxide. So what students do, this is drag and drop. This is sort of like an item bank. They can drag out of here, and here you can't really read it, but what's labeled is on the left side you've got methane plus water, on the right side you've got hydrogen plus carbon monoxide. Again, what happens to atoms during the reaction and how your model shows that mass remains the same during this reaction. So here's an example, so just as a reminder, here are the FKSAs. I've simplified them here. It's basically the idea that you can describe that mass is conserved in a chemical reaction, that atoms regroup in a chemical reaction, and that you can represent, you can use a model or develop a model that shows this conservation and regrouping of atoms. So those are the 3 FKSAs that underlie this. So here's an example task. And you can look through this task and see they've got a methane molecule, they've got a water molecule, they now have 3 hydrogen, and then they've got a carbon monoxide molecule also. If you were to add these up, they all add up to the same number on the left and the right side, so you've got the conservation of matter and you've got the regrouping of atoms. Then if you look through here, you would see that they explain that mass is conserved in a chemical reaction. So at the end they say, as for how my model shows that mass remains the same, the amount of atoms within the model remains the same, meaning the mass has not changed, but the ways that which the atoms have connected have. So they've also got that atoms are regrouping as well. So you can see here that it's got all of these aspects of these FKSAs. So this is basically a simplified version of how we score these assessment tasks themselves. So what we did with all of these data was that we coded these constructed responses. We used dual raters. So we had multiple people coding each task for features of the FKSA, and each FKSA becomes a rubric component. And then we just score those FKSAs as being either absent or present in the student's response. And then we can calculate a total score based upon the partial credit. So we can sum up over the number of FKSAs that are present, and that becomes the total score that they get. Okay, so here is how this student would have scored with this response. They would have gotten a 1 for each of those 3 FKSAs, and so their total score would have been a 3. Okay, so now let's take a look at what the item category function curves look like for this item. Now the curve I'm going to show is not for any specific answer. This is for all of the data, for all of the student answers that are here, where students sometimes get a 3, sometimes get a 2, sometimes get a 1, sometimes get a 0. And so you can see a nice separation there amongst these curves, so we're able to discriminate at different levels. You can actually then also, you can drop again these vertical lines. And what's really important in item response theory when you're using polytomous data is the thresholds, the transitions where you go from one curve to the other in terms of the higher probability. So you can see here that students sort of below the theta of 0 have a transition point between 0 and 1 that's at about -2. Then above 0 is where they transition from 1 to 2. And then at the top here, over 3 is when they can finally get full credit there. So this, again, lets you sort of see items and people on the same scale. So again, all of this is thinking about where the item difficulty lies along this latent dimension and where students' ability lies along this latent dimension as well. Crystal?
So what I think you just said, I'm asking, is so for a student to get full credit, they have to be a pretty high ability level
That's correct.
to get full credit on this one.
Yes.
But then this difference between like this transition from 1 to 2 and 0 to 1, that's a very small, is that like a very small range? Because it's like what, -2?
Yeah. It's not that small of a range, but you're right in that it's to the left of this 0. And so it is the case that students with some low ability can still get partial credit on this. And we don't know from these data, we don't know which FKSA they're getting right. And different students could be getting different FKSAs right. But even the sort of lower ability students are able to get some points on this item. Yes?
Yeah, that was the question in my mind, was that a 1 or a 2 could look really different, depending which FKSAs they're getting right and not right. Can you further disaggregate to look at all of those possibilities, or is that practical or impractical to do? Or?
So the question is, can we disaggregate those? And we can disaggregate those when we actually look at the types of responses that we're getting. So because we're coding these like this, then we could also separately look at how many students are able to get this one correct, or how many are able to get this one correct, or how many are able to get this one. We wouldn't be doing it using this IRT measurement model, but we could still look at that and do that analysis. That's true. And so that would be interesting to see what's the highest frequency of FKSA that students are getting right here. Is it their ability to develop the model, or is it one of their descriptions of that model? And then you could look at that not only just as a whole, but as a function of their total score as well, which would be really interesting to look at. Okay, let's look at another item. So the battery task. And here's a different sample student response. What you should notice right away is that the number of atoms is not the same on the left and right side of the equation, so they don't get the conservation of mass. If you look at their description, they talk about regrouping of atoms, but they don't talk about conserving mass or conserving atoms, and their model does not show conserving atoms or conserving mass. So again, this student is going to get a 1, so they're getting partial credit here. This is the same representation, but with this item. You can see that this item is more difficult. So here, for a student to get that transition from 0 to 1, they have to be at a theta level above 0 already. And what you can also see is that there's no student in our data set that's getting a score of 3 in here, which is why there's no category of 3. But you would assume if we did have some data, it'd be even further to the right here. Marianne?
Your rubric or your,
Mhm.
it's more like a check sheet, was that given to the students as they were doing their write-up?
It was not given to the students. That's a good question. So it was not given to the students. So we look at, if you look back at the prompt, we try to make sure that the prompts are clear and are eliciting all those different parts. So it asks them specifically, it tells them from your drawing, describe what happens during the reaction to the atoms of the water molecules, which is the prompt that if they know they're regrouping, they should be talking about that. It says explain why mass is conserved during the reaction, which Laura was talking about. So it's prompting them for that as well. So that's one of the places where we look at the alignment of the task to the evidence statement. And we think that it's not always going to be the case that students have the rubric. So we want to make sure that the prompt is very explicit in saying what we are expecting them to produce in their written description. So we didn't write something like, describe what your model shows. Don?
So this is additive, so students get a point for doing something.
Uh-huh.
Do you ever look and see if they're doing things that might be reasonable but are not going to garner them important points?
We look at that. We do not score for those. So our scoring model is very tightly tied to the knowledge, skills, and abilities that we've represented and articulated.
Mm-hmm.
And if it's knowledge that's important and possibly correct, but beyond those knowledge, skills, and abilities, we do not score for that.
So in terms of the task design,
Mhm.
I could imagine that that is an example of something where, to put it in terms of operational for the students get distracted. And they wind up spending time on something which is, again, valid for what they think they're supposed to do, but they're not actually doing it.
That could be the case. So that that speculation could be right in some of these instances. We work very hard to not design the assessment tasks to do that. And we use other things like cognitive labs or the expert reviews to try to forestall that, so that they're not getting distracted about other things that are not related, but that is a concern we have. Yes, Marianne?
One more question. So were the assessments then shared with the teachers so that they could use them as a formative assessment instead of summative?
So this is another great question. So this is a balancing act we're trying to walk. So we're developing the assessments so that they can be used by the teachers formatively. The data that we collected was in a data collection model, which is much closer to a summative assessment, where you're giving them, and that's only because we needed to collect a large amount of data in a small amount of time. So what we're doing now in the current data collection methods that we're doing, we are doing a better job of having the teachers integrate them into the instruction and collecting the data from them, using them when they're better integrated into the instruction. The downside of that is you have less control over which tasks get used. So one of the things we wanted in this study is we wanted to be able to get data on all 65 of the tasks. To be able to do that and ensure that with the small number of teachers and students we had to use this model of data collection. Yeah. Tim?
So you might have said this and I missed it, sorry if that's the case, but how is the latent dimension established? Is it overall performance on the assessment as a whole or on some other assessment? Or
So the latent dimension is established as their performance on the set of tasks that they're given. So it's not a separate criterion that we use. So it's their latent dimension is an estimation based on their performance of that set of tasks. One nice feature of IRT is that it allows you to administer different tasks to different students. And as long as you have some tasks that are the same between students, you can assemble all that data together. So this theta is really not the specific 3 or 4 tasks, but rather the 8 tasks that are there. Yes, Susan?
So is there some other independent way of establishing that they all in fact comprise a latent variable or not?
So there is. So one of the ways that you can also do IRT or in tandem with IRT is to do some factor analysis to see if there's multiple dimensions that are at play there. One of the assumptions of this IRT model that we're using is that it's a unidimensional assessment. So it is that overall theta is the ability of doing those 2 chemical reaction topics. You can also do multidimensional item response theory, which would allow for multiple dimensions in there. We haven't done that yet or investigated that. Yeah.
So something to come back to, not here, but just in general, there's the dimensionality going on with the three-dimensional NGSS.
The three NGSS dimensions, that's right.
There's the dimensions here of the learning performances.
Mm-hmm.
There's the latent variable in which that task cluster under a learning performance should all be measuring the same thing, but that's three things.
Mm-hmm.
Because it's the three performance dimensions captured in that, I forget what the right label is, performance indicator, whatever. That is, you got this complicated set of relationships, which if task 1 through 6 tasks are in fact all measuring the same, what is it, FSAK something, or
The same
FKSA,
set of FKSAs,
right?
yeah.
Then they're mentioning three dimensions of something integrated,
Mm-hmm.
but it's one latent variable.
Yes.
That's really hard to understand. So
Yes.
it-
I agree with you. We're still
Some
understanding.
unpacking. I know
Yeah.
you're teaching the methodology course, so I'm just saying that it might be worth a good discussion to go deeper into that.
And we've
What sense it makes, really.
Yeah, we've had some discussions on that. We have to keep having those discussions. I think a good question is whether those three NGSS dimensions are the same dimensions that you would get in some latent space, and I don't think they are. But that's not to say that we don't have multiple dimensions that are at work here. Raymond, one more question, and then I'm going to go on because I do want to wrap things up.
You're conditioning on the thetas and the betas.
Yeah.
So that means you estimated them somewhere earlier on?
The IRT does it in the machinery. It's estimating those simultaneously.
Okay. I'm not familiar with IRTs.
Mm-hmm. Okay, so let me show you what we've been talking. So we've been talking a lot about this latent dimension. So we've got this latent dimension here where performance. So what we're representing here is this is a histogram of students on the latent dimension. So of our students in this sample, we've got some students that are in the middle, a few students that are high on the latent dimension, and more students that are lower on that latent dimension. So we're actually able to, again, think about students in terms of where they are in this latent dimension, and then we can put tasks on that same dimension. And so we can see where any given task, so each of these is a different task, we can see how that spans across this latent dimension. So I'll look at these two that we've been talking about. So this is the battery task, and this is the methane task. And what you can see here, and what you could also see in that other representation, is the span of the latent dimension that is covered by that methane task is much wider than it is by the battery task. So this is just another representation and a way to see multiple tasks at the same time and compare overall the difficulties. So the tasks here further to the left are going to be easier. The tasks further to the right here are going to be more difficult. Did I see that?
Yeah, so are you going to comment about the third item and the seventh item where there seems to be, I don't know if inversion is the right word, but.
Yeah, let's say inversion or reversal here.
Yeah.
Yes, let's comment on that. So this one is a funky one. That's the technical term. And
Much better.
Why is that funky?
because
the most.
because the 4 is over here where you would think that the 4 should be over here. So let me show a different representation of this. So this is that task. And this is the set of item functions. What you'll notice here, and this is what I sort of warned us about before, one of our items, or one of our response categories down here has a very low probability and is not really, there's nowhere on this latent trait where it's getting possibly a probability of getting endorsed. The other thing, and I think I didn't show it up here, is the thresholds that I showed. So there's going to be a threshold, I got to point at it. There's going to be a threshold here. There's a threshold here. There is then a threshold up here, which is the 3, And then the 4 threshold comes all the way back here, which is why we got that reversal of the 4.
What threshold of what?
So it's where they cross?
The threshold where these curves cross, where they intersect. Where it's the threshold where you would, given your latent ability level, if you go above that threshold, it's going to change the probability of getting a certain response. So you're going to go from 0 to 1 or from 1 to 2.
So that's a function of the fact that 3 is so
No,
So
decrepit.
unlikely.
It's a function of,
If there was a greater probability of getting 3s, then that would bring that threshold to the right, which is where you'd expect.
yes, well, it would bring it higher. I'm not sure if it would bring it to the right, but then you would want this one to go further to the right. The
Yeah.
problem is that the students that are getting 4 are getting estimated lower on their latent ability level.
Mhm.
Raymond?
So the only thresholds that matter are ones that are above everything else, in the sense that there's no threshold below that, like directly underneath, or there's not a, so you see where actually when 0 and 1 go, they're above everything else.
Uh-huh.
But the threshold where the purple and the light blue are below things of higher probability. So you might not even pick them up in just a data table, so you might not even notice where that threshold is.
But it does, because that's where it looks funky on the graph. That was why the 4 was way back there,
Yeah.
because it was just counting where the 4 and the 3 crossed without knowing that they actually weren't, that's not actually where 4 was.
Okay, that's,
Can we go back one slide for a moment? So on the one we're talking about, the 4 being all the way to the left of the 2 doesn't mean that students who had lower latency were more likely to get a 4 than students who had a higher latency. It's just that the cross was there.
Let me see if I'm understanding the question. Are you saying that the 4 being there means that the student with a higher ability, with a lower,
Lower ability has a higher probability of getting 4.
That's how
yes,
I read this
yeah,
one.
and that's what these data are showing. So that is the correct read of these data.
But the
But it's
4
not
is so
actually-
high.
Isn't that a misleading part of how it factors into making that version? Because like, it's just because in real life you're not actually, it's highly unlikely that anybody's gonna get a 3, right? Is that what
Well,
you're
so
saying?
let's look at it's in our data that we're using to model these, it's unlikely that students are going to get a 3. It's also unlikely in the actual data that they get a 4. So let me just, I'm just going to do it. I'm just going to show it. So in our data, we basically have one student that gets a 4 and one student that gets a 3. And that's what's throwing off
And
this.
that generates that pattern?
Because this student with getting a 4 has a lower ability level estimate. So they got a 4 on this item, but their overall level is lower. Yeah.
Is that also affected by the fact that you had fewer students with a positive latency than a negative latency? If I'm interpreting that bar graph on the top that you had?
No, I don't think that necessarily is affecting this reversal.
Because, like, you only have one student who's got a big latency. So is that why that student got the 4, and that's why that 4 is so high in your...
No, it's actually the
Correct.
opposite. It's that a student around here got a 4,
Oh, okay.
which is throwing it off.
Also, it's not a latency as in delay of response.
Yeah.
It's like some measure on whatever that latent dimension is.
Latent trait.
Okay,
Yeah.
thank you.
So then, is there another way of interpreting that information, that particular item is not does not map to what you would have predicted in terms of performance out of these set of students for which you calculated?
Yeah, so, so from this analysis, that's right, this is not what we would expect. From then looking at this, it seems like it's not a function of the item itself, but the data set that we have.
So, okay.
Yeah, because we have so
Such
few
numbers.
here, right here. Alexa?
Do you, and this may not be something that you can answer, but is it likely or at least possible that some of this would be different if it was getting used in its intended sense as like closer to instruction? Like would these scores end up being different so that you would end up getting different curves potentially if each item was getting used more like when it was actually getting taught in class than
So
all
we-
clustered together?
We might see shifts. You might hypothesize that if it's being taught with instruction, you might have some students that are higher ability over here. That would then I'm not sure if it would shift these curves to the right or not. I don't know.
I mean, you wouldn't have as much of an issue with the couple only
That's,
two kids getting
that
really
part
high.
is
So
right.
you could,
Yes.
it would be clearer what the
That
actual
part-
patterns
Yes, that's right. Yeah.
were. Okay.
Okay, let me give a couple conclusions. We can have some time for questions since y'all were so shy. So conclusions, items have a range of difficulties spanning a wide spread of the latent trait. Most items, not all, but most items showed a desirable response pattern where we have monotone increases in the probability with increasing ability estimates. Overall, the items are more informative for students with higher ability, which is potentially a function of the sample that we've got. And then we found support for our inferential validity claims that the rubric scoring we've used yields recoverable item performance information to where, for the most part, we can see different levels of student response patterns that correspond to different levels of ability. So just to put kind of a neat bow on the package, we've seen a principal design approach that provides one source of validity evidence, and that's for the cognitive and instructional claims, and it allows us to focus on the integration of multiple dimensions, this sort of knowledge and use that we've been talking about, and look at multiple components of student proficiency. The measurement modeling we've done provides another source of validity evidence for the cognitive and inferential claims. In particular, the scoring approach that we're using seems to be a valid way of taking these FKSAs, using those to create individual rubric components, scoring those for the presence or absence of those features, then using those to build up to a total score, and that then allows us to see distinct levels of proficiency. Just as a side note, as I said towards the start, we think that this design approach and measurement model can apply equally to assessments in other disciplines and with other age ranges. So one area we're interested in going is into engineering at the undergraduate level, where you've got students also engaged in these engineering practices with this science of engineering knowledge that they have to do, and trying to create some assessment tasks and get some data around those as well. So thank you very much. Great questions.